The Chernobyl disaster was the most devastating nuclear reactor accident in history. How does a power plant work, and how did it turn into a nuclear bomb? Nuclear power plants provide us with electricity in our daily lives. Around 11% of the world's electricity is generated by 450 nuclear power reactors. Some 60 more reactors are under construction, equivalent to about 15% of existing capacity. Yet the world's first nuclear reactor was used not to generate electricity, but to make nuclear weapons. A reactor works by triggering a chain reaction, which keeps releasing energy at an exponential rate. To achieve the chain reaction, we bombard an atom of uranium or plutonium, the nuclear fuel, with a neutron. When the neutron hits the atom, it becomes unstable and falls apart into lighter elements. 2 or 3 new neutrons and a huge amount of energy. These 2 to 3 new neutrons go on to hit other uranium atoms, which each release new neutrons, and so on. The result is an exponentially increasing reaction rate. This is what we call a nuclear fission chain reaction. This principle is used in both a nuclear bomb and a nuclear reactor. Of course, this doesn't happen with just any piece of uranium. First, the fuel needs to be of the right density and in the right amount, called a critical mass. Second, we need highly enriched fuel. Uranium comes in 2 common isotopes, uranium-235 and uranium-238. Only uranium-235 is suitable for chain reactions, but it's pretty rare, comprising only 0.7% of naturally occurring uranium. Enriched uranium has a higher than natural percentage of uranium-235. For a nuclear reactor, about 20% is sufficient, but weapons-grade, highly enriched uranium, HEU, requires at least 85% uranium-235. Synthesizing HEU turns out to be the most difficult part of building a nuclear weapon. Another popular nuclear fuel is plutonium-239, which has its own complications. It's exceptionally rare and can only be synthesized from uranium. Do you remember the Fermi paradox video? Fermi presided over the construction of the first nuclear reactor, Chicago Pile 1, aiming to synthesize plutonium-239. We all know that the Manhattan Project made the world's first and second nuclear bombs. These 2 nuclear fuels produced different nuclear bombs, Little Boy and Fat Man. Scientists soon realized that, because of the vast amounts of heat released, the nuclear chain reaction could be used to generate power if only there was a way to control the reaction to prevent it from exploding. In 1954, the former Soviet Union found a way and built the world's first nuclear power plant in Obninsk. It served as a model for several others, including Chernobyl. To do this, they first needed to control the reaction. The solution is essentially to absorb some of the excess neutrons so that the reaction doesn't develop exponentially. This is done by adding material in the form of control rods that absorbs neutrons but doesn't otherwise react with it. The control rods are inserted or removed from the reactor to control the rate of the reaction. Secondly, they solve the problem of needing highly enriched uranium. They found a way of relying on enrichment of just 2%. It turns out that a lower energy neutron has a higher probability of causing fission. So, instead of further enriching the fuel, they managed to lower the energy of the neutrons released in each reaction. This is done by inserting a material which does not absorb neutrons. It only slows them down. This technique is known as neutron moderating. Keep in mind that inserting a moderator in the reactor will slow the neutrons down, but this actually increases the rate of reaction. Heavy water and carbon, in the form of graphite, are both moderators. Heavy water is mostly identical to regular water, H2O, but has a heavier isotope of hydrogen called deuterium, D2O. In the RBMK-type reactors installed at Chernobyl, regular water, not heavy water, is pumped through the reactor, absorbing the heat generated by the reactor, cooling it and generating steam, which is then used to drive the mechanical turbine connected by the same shaft to a generator that produces electricity. The big advantage is that it's cheaper to build and operate this reactor type, because the enrichment of uranium doesn't need to be very high, and it uses regular water instead of heavy water. However, this came at the cost of several fatal design flaws. Heavy water acts as a moderator, so it increases the rate of reaction. If the reactor starts to overheat, the heavy water will evaporate, creating a void. If there is less heavy water, the reaction will automatically slow down. But an RBMK reactor uses regular water, which is also a neutron absorber. When the temperature increases and the water evaporates, light water's neutron absorption capability practically disappears. This allows more neutrons to react, thereby increasing the reactor power, which leads to higher temperatures that boil even more water, creating a thermal feedback loop. Positive feedback. This flaw increases the control difficulty for the system, especially when the reactor is running at a low power level. So, some of the security measures at Chernobyl was to forbid working at lower than 20% full power, 640 megawatts. The second flaw is with the control rod design. As we know, control rods and moderators have opposite effects. Removing a control rod, an absorber, has the goal of increasing the power of the reactor. To boost this effect, they attached a piece of graphite, a moderator, at the end of the control rods. This way, when they pulled out a control rod, it was replaced by a piece of graphite. Why is this dangerous? Well, if you wanted to slow down a reaction by inserting a control rod, the bottom of the rod will move some water, an absorber, out of the way, replacing it with graphite. So in the first couple of seconds, the power will increase. The last element is that the reactor did not have a containment structure because of cost-cutting measures. Normally, the reactor was deemed safe enough for regular operation. However, these factors would come together to set in motion that fatal day. On the 25th of April 1986, the Chernobyl nuclear plant underwent a test, a simulation of an electrical power outage. They wanted to know if power to the water pumping system were shut down, what would happen to the steam turbines in operation? Would they have enough residual energy to power the system before the backup diesel generators kicked in? As the backup generator was designed to start up within a minute, the reactor was not shut down. This test was supposed to be run at a low power level, between 700 and 800 megawatts, and in the daytime. But when the power was decreased to half in preparation for the test, 1,500 megawatts, there was a sudden request from Kiev for the test to be postponed to the night. As such, the test fell into the hands of another operations team, which had not been prepared for the task. At 23:04, the test resumed, and the operators started to lower the power again. However, one of the fission byproducts, xenon-135, hadn't burnt off quickly. Xenon-135 is an excellent neutron absorber, and under normal circumstances, the operators would account for this effect by regulating the control rods. For this reason, xenon-135 is called a neutron poison. Xenon-135 is burned off by absorbing neutrons. However, when the reactor power is turned down, the already present xenon-135 can't be burned off as quickly, increasing the amount of neutron absorbers and slowing the reaction. And because of the lower temperature, there was more water rather than vapor than usual, which had a further negative effect on the reaction rate. Because of this, about an hour into the test, the power suddenly plummeted to an extremely dangerous level of 30 megawatts. Control room personnel decided to increase the power by disconnecting most of the reactor control rods from the automatic control rod regulation system and manually extracting almost all of the rods to their upper limits. Removing the control rods increased power back to 200 megawatts, So they decided to do the test at the 200 megawatt level. Because of the low operating power, the water levels were not sufficient. As part of the test plan, extra water pumps were activated to increase the water flow. And to counteract the absorbing effects of the water, they removed more manual control rods to maintain power. At this point, the situation got out of hand. There was more and more vapor void in the water, which accelerated the reaction due to the positive void coefficient. When the operators saw this, they activated an emergency stop by inserting all control rods at once. But when the control rod was inserted into the reactor, the graphite tip was displaced downwards, shunting that water at the bottom out of the way. However, that 1.25 meters of water was absorbing neutrons. When replaced with the graphite as the control rods moved downwards, the reaction rate at the bottom of the reactor actually increased temporarily. The reaction also increased temperatures and pressure inside the reactor far beyond the design limits. The moderator, graphite, is a highly flammable material and effectively acted as an extra fuel. Eventually, the pressure inside the reactor was so high that it exploded, blowing the roof off the reactor. Because there was no containment structure, the radioactive residues from inside the core were blasted into the atmosphere and leaked into the soil. As a result of this disaster, several modifications to the RBMK reactor design were made, including fixing the problem that graphite caused when inserting the control rods and improving the emergency shutdown process. Newer generations of power plants have learned from this accident and incorporated more safety measures and containment structures in their designs. But the damage from Chernobyl spread far and wide, all over Europe, and has lasted decades, as far north as Sweden and Norway and the Scottish Highlands, releasing hundreds of times more radioactive material than the Hiroshima and Nagasaki atomic bombs. It goes to show that nuclear security is not just a matter of national interest or national pride. It is of crucial concern to the whole planet. Thanks to our friend at Mummy Talk for the inspiration.